Okay, so far in class we've looked at heat of reaction in terms of Q equals mCp delta T. That is one way to determine the heat of reaction for a given reaction, but there are other ways to do the same thing. One of them is by using something called standard enthalpies of formation, or sometimes it's called standard heat of formation. Okay, first of all, standard refers to the conditions that we're working under. Standard conditions for thermodynamics, 1 atmosphere pressure and 25 degrees Celsius, 1 molar solutions. These would be regular working conditions in the lab. This is different from STP for gases because STP for gases is 0 degrees Celsius. And no one wants to work in the lab that's at 0 degrees Celsius. It's much more comfortable to work at 25 degrees Celsius. So when we talk about standard heats of formation, the symbology looks like this. You'll notice you have delta H with a little degree sign. The little degree sign means under standard conditions. So this delta H would be for any reaction. Standard heat of formation. So if I'm talking about heat of formation specifically, you see that little lowercase f is defined as the heat of formation of a compound from its elements. So if I'm looking for the heat of formation of methane, which is CH4, that would be carbon plus 2 hydrogens to yield CH4. I would calculate the delta H for that particular reaction, and that would be called the heat of formation reaction for CH4. So because heats of formation are deltas, so they're relative, we define the heat of formation for any element in its natural state as 0 kilojoules per mole. So elements exist, and then we base the heats of reaction for compounds based on the fact that elements exist. Okay, there is a heat of formation table that can be found in Appendix C in the book if you're doing work at home, and I did not give you values in the problem. In class, I will have tables for you for heat of formation values. So the way this works, the heat of reaction for any given reaction is equal to the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. So what does this look like? Again, all we're going to be doing, this would be my x, here would be some values. So I plug in the numbers and solve for x. So let's look at a couple of different problems that we could do. Okay, here's the first one. Here's a table of heat of formation values. You notice it's in kilojoules per mole. And I want to calculate the delta H for this reaction that is listed. So delta H is equal to the sum of the products minus reactants. So the delta H for the reaction is equal to the sum of the products. So let's see, the first product is aluminum oxide. Its heat of formation is negative 1676. Plus, now I have aluminum chloride. Aluminum chloride is negative 704. Plus, I have nitrogen monoxide, but you'll notice there are 3 of them. Since this means there are 3 moles of nitrogen monoxide, and this table is for 1 mole, I need to multiply the heat of formation by that coefficient, which would be 90.0. Plus, now you notice H2O, there are 6 of them. So I take 6 times the heat of formation of oxygen, of water, excuse me, not oxygen. So that would be the heat of formation of the products minus the heat of formation of the reactants. Aluminum is 0 because it's an element in its natural state. So the only thing I'm going to subtract from that is 3 times the heat of formation of ammonium perchlorate, which is negative 295 kilojoules per mole. So I add up all my products, and then I subtract the reactants. When you do this math, you get negative 2677. And that units of this would be kilojoules per mole reaction because it's for a whole reaction. Now, in terms of significant figures, since I have addition and subtraction here, I'm looking at place values. So you'll notice everything goes to the ones place except for nitrogen monoxide, which goes to the tenths place. So I'm allowed to carry digits to the ones place in this case. So that would be solving for the heat of reaction. Another variation on this, and actually the only other variation, is to move x into the right side of the equation. So in this case, in this reaction, I know what the heat of reaction is. It's negative 2,800 kilojoules. So I know what that is, and we'll just put the number up there. What I'm looking for is the heat of formation of that one reactant. The equation is the same. Delta H equals the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. So let's look at our products. We have 6 CO2s. And, oops, we need to add in the water. Plus 6 H2O. Now, you'll notice for water, there are actually 2 different heats of formation values. This heat of formation value is for liquid water. In the last table, we saw the heat of formation for water if it were a gas. Because remember, there's a heat difference between liquid and gas phase. So you need to pay attention not only to what the substance is, but its state of matter as well. So here are my products, and from that, I'm going to subtract the reactants. Oxygen is 0, so we don't worry about that, and there's only one C6H12O6. I'm going to call that X. So now, instead of X being over here, it's over there. Same thing, we just solve for X. The other thing you need to pay attention to in these problems is signs. Positive and negative, remember, not only does it have an algebraic meaning, but it also has a meaning in terms of is heat flowing from the system to the surroundings or from the surroundings to the system. So if I rearrange this and solve for X, I get X equals negative 1275.8. That's what's in my calculator. Looking at significant figures over here, this 2,800, we have addition and subtraction pretty much, so I have to go back to the hundreds place, so that would be negative 1,300 kilojoules per mole